As per usual, a lot of these multiple choice solutions will repeat, and that's fine because they end up being repeated on the AP. So we want to know which of these corresponds to the motion of an object moving in a straight line with positive acceleration. I hope by now you're clear that that's choice D, that that's the parabolic motion. Here we want to know about displacement. So again, the answer, we are starting 2 meters above the ground. We go up here, and then we wind up on the ground here. So our displacement is 2 meters below where we started. Acceleration and velocity are both vectors. They have size and direction. A scalar means just a number. They do not have the same measurement. And they are totally not different names for the same quantity. It is absolutely choice B. Okay. Now, here we have two projectiles launched at the same initial speed from one location, one at 30 degrees, one at 60. They land at the same height at which they are launched. So we want to know which one goes up higher. So let's just figure this out. So the height is going to be v naught squared sine squared theta over 2g, sine squared theta over 2g. And the time is going to be v naught sine theta over g. So if we actually apply our, I kind of had these formulas memorized, didn't I? So if we want to come up with them, we could say v naught sine theta, just to get the time. So v equals negative gt plus v naught. Half the time, 0 is negative gt plus v naught sine theta. So actually the time is 2 v naught sine theta over g. And then to get the height, that's going to be v squared equals v naught squared plus 2g, plus 2g h. And then here we got 0, and this is v naught squared sine squared theta. So yeah, v naught squared sine theta over 2g. So it looks like the height and the time should actually be longer or whatever, bigger for the 60-degree one. So let's rule out the ones that don't work. Let's just take it one at a time because I'm a little tired. That's not going to work. That's not going to work. That's not going to work. So it's either D or E, and it looks like E is the choice that works. That actually makes sense. The longer you spend in the air, the higher up you go. So an object of mass 100 kilograms is at rest on a horizontal surface. At time t equals 0, 10 Newton force is applied. And we want to know for 1 second, so after it's removed after 1 second, we want to know what happens. So remember, we're on a frictionless surface and we've stopped pushing. What that means is, no, it is moving with constant, no, it's no longer accelerating. It will not come to rest because there's no friction. So the truth is it is moving at a constant speed in a straight line. Okay. Now, let's talk about objects in equilibrium. Several forces act with the objects in equilibrium. We want to know what's true. It will definitely have zero acceleration. The net force is absolutely zero. But we really can't be sure whether it's at rest or moving at constant velocity. So really, A is the only choice here. A rock dumped from the edge of the cliff. We're assuming projectile motion. So let's just right away, since we know it's projectile motion, let's eliminate some choices right away. We know that there is no possibility of the acceleration being zero ever. So that rules out C and E. Now let's read a little bit more. At point P is the highest point in the rock trajectory, and at point Q we're level with the starting point. We want to know the horizontal and vertical speeds and the acceleration of the rock at point P. So at the top, we know that the vertical speed is 0. We also know that the horizontal speed is unchanged, so the only choice left is A. Now, the acceleration of the rock at point Q, let's be careful. Once again, 0 acceleration will not work. The horizontal speed still needs to be there. But now we're at Q, so the vertical speed has been regained. It's, of course, if they said velocity, this would be negative, but we're only talking speed, it's magnitudes for choice D. And then problem 9. Ooh, kid jumps on a sled, a little momentum problem there. So, what's the mass of this kid? 20 kilograms. What's the mass of the sled? 5 kilograms. And we want to know their speed after. So we got 20 times 4 plus 5 times 0 equals 25 times the final speed. That's going to be 80 equals 25 VF. So 80 divided by 25 is VF. So that's going to be 16 over 5, which has given me 3.2 meters per second. I skipped a lot of details. I would like, please set up using conservation of momentum. I'm going to leave that to you. And I'm going to be a little mean here. I want you to look up conservation of momentum. We've done it in the notes. You can also look it up online if you haven't kind of digested the notes yet. And then I want you to get to this answer given this little guide that I've given you here. All right, a toy spacecraft is launched upwards. When the toy reaches its highest point, springs release. The toy splits into two parts. This is clearly momentum conservation. So we've got this toy. We've got 0.2 and 0.8. Now what's going to happen? The 0.2 moves east, and the 0.8 is going to move west. So let's be clear. If it's moving east, there's no way we could move to the north because momentum wouldn't be conserved. Takes longer to reach the ground, the 0.2 part. No, they land at the same place. Here it says it strikes the ground farther from launch. I'm getting none of the above. Wow. It's interesting. It's, believe it or not, the answer is A. It will not strike the ground farther from launch. It actually strike the ground closer because it should have lesser speed if it's got a bigger mass to keep momentum conserved in the horizontal direction. Weird. All right, so we'll take a look at 10 through 20, or at 11 through 20 the next video.